So, first of all, many thanks for setting up this very nice workshop in this marvelous place. I haven't been here before, so that was also great to come here for the first time. Now let me start straight away. What I'm going to talk about today is essentially giving you an introduction and overview over some of sort of the most important aspects of non-stable fixed points in the context of universal dynamics and its relation to quantum turbulence. And I'll give you some information about recent results from experiments as well, which could be achieved together with colleagues in Heidelberg and Vienna. Now, sit back and relax. That's what I'm always having this introductory slides for. And with this introduction, let me start straight away into the matter. Now, universal dynamics, there's universality in there. Now, when it comes to universality, what we think of in this context is the universality you have in critical phenomena. Yeah? So without going too much into the details of renormalization group theory and so on, let me just point out sort of the most important aspects. When you talk about universality, what you're thinking of is usually something like self-similarity near a critical point. So near a phase transition, for example, a second order phase transition, like you have them, you have it in the Ising model in d dimensions. And typically, in order to describe that, how you start off with is some Ginsburg-Landau type theory. Now, I haven't switched on my laser pointer here, but probably it's not. I can just use my hands. Is there another one?
There should be a stick there.
Oh, a stick, yeah. Plastic pointer is great.
I'll grab one. Oh, it's right here.
Oh, it's it. Yeah. Right. So you start with this Ginsburg-Landau type of description where you write down a potential which has either a single minimum or in the broken symmetry phase degenerate minima, and the system in this broken phase then in a spontaneous way takes on one of the minima, kind of developing an expectation value of the order parameter, and thus going over, distinguishing clearly between the two different phases. Now, the transition in between, this is where the universality takes place. And the way one is usually describing this is in terms of flows of effective models. So what you want to know is actually what are these constants. So if R is negative, it's clear that for a positive coupling U, you have two minima, whereas when R is positive, you only have a single one. So R switching over from positive to negative numbers in this sort of simple microscopic approximation describes the phase transition. Now, taking into account in a full interacting system all the dynamics and fluctuations in quantum mechanics, the quantum fluctuations as well, this will not be the full story. So what you need to do is you need to renormalize these couplings, take into account all fluctuations, and then ask whether at a certain scale at which you look at the system, these couplings are still as they are in the microscopic case, or what they actually are. And this is what your RG flow describes. So when you go over from some microscopic scale to the macroscopic scale you wanted to describe the system at, you will find that the couplings flow according to some RG flow equations, and then they may trace out the space they are allowed to live in. So here's sort of an example of the coupling versus this mass scale. They trace it out in a very specific way with the possibility to hit these fixed points. And here are two examples: the Gaussian fixed point, which is at zero coupling, which applies to the Ising model in d greater than 4 dimensions. And then below this upper critical dimension, this fixed point actually develops, so shifts into the positive U plane, and it happens somewhere at a finite U. So this is kind of the typical form which you get when you look at critical phenomena. Pardon?
Yeah, a question. You see, so
yes.
when you're saying this, you're in the microscopic theory.
Yes.
At that point, R and U are 0 in your case, or they're very small?
Well, it depends on yeah.
So what's the assumption there? So you start with very small values, and then you introduce a cutoff, lower the cutoff, and then you run towards those points.
Well, you define your couplings at some microscopic scale at which you know that's what let's say sort of the interactions between the fields here, the particles or whatever you look at, and the mass scale, and then that scale, of course, is set by the particular physical problem you have, and then you run your RG into the infrared. And during that running, this flow can become universal, actually forgetting about these microscopic details, which then become unimportant. Yeah? So once, let's say you tune in an Ising model the temperature. Yeah? So what you then typically do is you tune this R. Let's say you start somewhere in this plane. Let's say you're far away from the fixed point in the microscopic regime, and let's say you fix U and then tune R along this regime. And then you run after that your RG equations. Now, depending on whether you started below or above this kind of critical line here, you end up in the end somewhere up there or somewhere down here. Whereas actually the coupling U flows very close to this line, which actually hits here the fixed point. So also, when you are sort of starting somewhere on the critical line, you will run exactly into the fixed point.
So if you're above the line here, you'll always end up with a repulsive model. There's no minimum.
Absolutely. Yeah, and if you start below, you end up down here. Of course, the further you're away from this critical line, the less universal you are in the end, because you are actually getting away from the fixed point again. But when you are coming close to the phase transition, so to this sort of starting point here on the critical line, you will stay somewhere in the vicinity of this fixed point, and this is where actually scaling happens.
And if you are below that line, so you go along this line and you go to minus infinity?
Well, eventually you would in an infinite system. You would go to sort of minus infinity, but of course in practice you never have that. Pardon? Yeah. Yes, essentially. But that happen. I mean, that assumes that your system has to become infinite, because this is an infrared flow, which means you go to larger and larger length scales. And typically, of course, in a physical system, you end somewhere at your volume.
Which only take the limits, the size of the system.
Yes, so the flow will always stop somewhere, at least at the size of the system. Now, if you're not precisely in this vicinity of this critical line, you will flow away and will be non-universal. And only when you fine-tune to this line, then you run and stay even in your large size somewhere in the vicinity. Yeah?
So then if you start with a microscopic theory, you flow to some scale, then are the parameters of that scale in some sense are the best parameters for tree-level modeling of that theory at that energy scale? Is that one way of interpreting this?
No, I mean the flow already is far beyond tree level, yeah. So
right. But then when you sit at some point on there at some cutoff or at some energy scale, then the parameter values that you have at that particular point, is that sort of the best tree-level approximation for that system? I mean, obviously, if you probe higher scales or lower scales, they run, but sort of
that's how you can see it. Okay, so actually, let me just take this as a picture in the beginning. So what you should keep in mind is there are points in the plane. If you run into those at large scales, you become universal. You forget about the details where you started from with. You forget about what you chose in the beginning. All what matters is the properties of this fixed point, so it's the way, sort of how the flow goes in this vicinity, in which will essentially then incorporate the critical properties like exponents and so on. Yeah.
So that fixed point appears if you look at large scales.
Yes.
But if you look at small scales, then probably it'll be somewhere else in the plane, correct? So it depends, you see what kind of microscope you have, right?
Yes, I mean, in this case,
low resolution, you'll see different.
Yeah, I mean, this is the example for the infrared flow near the phase transition of the Ising model. Of course, if you sort of look at universality at high scales, starting at a lower scale at the UV fixed point, the structure in the end is the same, but you would have to.
No, because if I go, you see, I go up and R becomes positive. Yeah. So I don't have a minimum.
Yes.
Right?
Yes.
Just say that this is what I meant.
Then you are in the symmetric phase.
In a way. You see, in one case I have a minimum, in the other case I don't.
Absolutely.
Okay. Thank you.
Right. So we won't need all the details from this kind of Ising model in the following, but the idea is essentially the same when we now go to non-equilibrium, namely that we ask for the possibility of universality in the flow of the system now, however, in real time. So we have in mind time evolution of systems. We do not necessarily have in mind phase transitions, although these fixed points will certainly be somehow related to equilibrium phase transitions, which we can discuss maybe further to the end. But now let me first of all set up the idea of having a non-thermal fixed point in the time evolution of a system with many degrees of freedom. So I'm having in mind the same thing as on the previous slide, namely that I can reduce the complexity of the system to a simple picture, let's say to a graph in 2 dimensions where I have two relevant or two flowing couplings. Whether they are relevant or irrelevant is another question. So let's assume I can reduce it to that simple plane such that I can actually picture it here on the screen. Now the question is, starting with some given initial condition, wherever it is in that plane, where do we run to?
So the notion of quench is respect to which randomness?
Pardon?
The quench, the notion is respect to which kind of randomness?
I'll give you some examples later on. Yeah? So at the moment, I just have in mind I can prepare my system somehow by a quench or by driving it or however, that it starts in different corners of my configuration or phase space. That's all I have in mind. It's very, very general at the moment. Yeah? So whether I can write this down in terms of couplings like the Ising model is a completely different question, which we can also discuss afterwards. Here, don't give these parameters too much physical meaning at the moment. Yeah? So all I would like to argue is that typically exactly something like in these universal evolutions in equilibrium happens also in equilibrium, in non-equilibrium. Yeah, so starting from some initial conditions, different initial conditions depicted by these blue lines, what I'd like to now illustrate is that typically the system actually very quickly loses, at least partially, the information about these initial conditions and moves towards a line in the close vicinity of a line which then eventually drifts to a single point at ideally infinite times. So in quantum mechanics, you can always imagine that in a way that you say, okay, there's a many-body density matrix. It loses via dephasing the information about the off-diagonal coherences, and that brings it very quickly in the vicinity of a diagonal density matrix, which, however, does not need to be thermal in the first place. So people have discussed generalized Gibbs ensembles and all this stuff.
But now it becomes more complicated because you run the scale,
yes,
but at the same time you run the time.
Yes.
So you'll have two running things,
yes,
instead of one.
Yes.
So you're going to discuss that particular.
I will discuss it in more detail. Yeah? So
this point you might appear in one limit.
Yeah. Yeah, so the of course important is beforehand the scale was somehow an artificial additional scale you put in your RG flow. So it's kind of, for example, the resolution scale of your microscope. Whereas here now, I have in mind that the flowing parameter is really time.
So this is the big time.
Yes.
Okay. With frame lines, first you take the time limits and then the scale?
No, I think it fixes the scale.
So you fix the scale, then take the time. It goes to infinity and then the scale.
I just have a usual time evolution in mind.
Scale fixed runs the time.
Yeah. Okay. Well,
I think that this is the picture.
Wait, so just think of a many-body system which runs in time. Think of correlation functions which depend on space and time, and that's it. Yeah, no extra scale introduced. We could do that, but for the first it complicates the picture. Yeah, but we can discuss that later on, how you could sort of set up a similar thing as in RG, including an additional scale which runs. Yeah, but I don't need it at the moment. I just need time in itself. You know? So what I'd like to argue is that this kind of line of, I would call them partial fixed points, where you see, where you can already see scaling or approximate scaling, this is associated with conservation laws, which the system needs to fulfill. So, for example, if you have a closed box and a gas in there and you bring it out of equilibrium, then for sure there are conservation laws like the particle number and the total energy, at least if the system is sufficiently non-relativistic. Now, what I'm saying is that we approach these kind of line of partial fixed points and then slowly drift along them. The system looks like it scales already or does it in an approximate way, and eventually it will run into a fixed point, which is still not a thermal equilibrium state, but which I call the non-thermal fixed point, or it won't, depending on sort of how close it got to that line. Yeah? So if it's sort of only running very close to the line, then eventually you can also deviate and run into the final thermal state without really hitting the non-thermal fixed point. And that'll be then, of course, also in a generic system, always the normal situation. The picture is supposed to be the full picture in the full fluctuating theory. It's not a classical approximation.
There are fixed points in the theory, real fixed points in the theory, which are not thermal in the quantum.
Yeah, so now you're absolutely right. The non-thermal fixed point itself will be very, so the fixed point itself will be a classical fixed point as any second order. So in these examples, I know at least this is how it is. It's infrared fixed points I'm looking at. And these infrared fixed points are typically classical fixed points, like a second order phase transition or the quantum critical point at 0 temperature. There can be then, of course, quantum fluctuations around them, but at the fixed point itself, I would not expect that there's quantum physics really important.
But, I mean, if you let this system evolve long enough, don't you expect that it's going to go to quantum?
Yes. Yeah, that's why I said at the end of my last sentence, the normal case, or probably the necessary case would always be that the system departs from this red line before it actually hits the fixed point, because you will have to put actually infinite energy into the system in order to reach the fixed point. That's a kind of a fine-tuning problem. In a finite system, it will always depart, and then quantum fluctuations will become important for that.
Just understand it better. So this applies also for any dynamical system.
Yes.
So the fact that you have another fixed point means that the system is non-ergodic.
That it is non-ergodic, you're saying? Yes. The fact that so if you would be able to hit this fixed point precisely, it would be non-ergodic. That's right. Yeah. But so that already gives you another idea of sort of what the problem is.
In that arrow to thermalization, that would be finally to say quantum, because it's So what I always expect in any practical situation, the evolution will run along here and then at some point deviate and symbols. And the least, so the minimum constraint which forces this is that we are looking here at infrared fixed points, but they will never be completely separated from UV physics because of conservation laws and the like. Yeah? So at some point you hit your quantum fluctuation scale or whatever at UV, and that will make you depart from that. But I will illustrate that later as well, that you understand why that is.
I'm sorry, but I don't understand the math. See, so let's assume that I'm close to the middle blue line on the left.
Yes.
But not exactly on it, and they don't hit the red line. Mm-hmm. Then I turn up, right? Mm-hmm. But then it looks like I come in conflict with the next blue line, which goes down. So
but actually, I do not want to imply that these blue lines exactly hit the red line. They will just come very close.
Oh, so all of them, they come close.
They come very close, and then
they will go along the green line, all of them.
Yes.
Okay, thank you. Okay.
And you need infinite energy to get to be on that red line?
I will show you in a minute why. Yeah? Okay, so the other thing is, I mean, realistically, you can hope to get to this red line, close to that. Right, now let's actually give this a little bit more meat. for this, I'd like to have a look at correlation functions, simple correlation functions, two-point functions, distribution functions actually in momentum or energy space. And the simplest one, for a Bose system is the Bose-Einstein distribution of number of particles in modes with energy omega, now here drawn on a double log scale. For a temperature and a chemical potential in a regime where, let's say, the temperature is already very close to the condensation temperature to a Bose-Einstein condensate, because in that regime we have actually the negative chemical potential scale being smaller than the temperature scale. There's a Rayleigh-Jeans regime. Below that chemical potential it becomes flat, and the UV cutoff is essentially the temperature. Now, when you cool down the system a little bit further, you will get the same type of curve, of course, just with slightly shifted parameters. So lower temperature, lower negative chemical potential, you're getting closer to the transition. But the shape of the curve is the same. Typically what one does is one sort of cuts off the highest energetic particles, and then the system rethermalizes, setting it to these lower temperatures, but leaving the shape invariant. So the shape is actually universal. The full curve is universal with just a few non-universal scales in here, namely the temperature and the chemical potential.
What's the point of double law?
Pardon?
What's the point of that double law? But the shape is that one, you see, which is the formula anyway. So.
Yes, you see it, of course, in the formula. Why do I show double log? I will show always double log in the following in momentum space. That's the first reason. And the reason is simply because we now see clearly that the shape is the same, which you would not see in single log. Now you see the whole thing is just rescaling, so it's shifting to the left and upwards. That's all. Yeah. So a rescaling in a double log graph is a shift along the two axes. Okay. That's why I'm doing it. Yeah? So the shape is universal, and the cooling is just the rescaling of these scales, which rescales the curve in a way that it shifts them to the left and upwards. So exactly the same I have in mind now for my time evolution, and I forget for the first about this UV part, but just look at the power law here and at the plateau. Now, when I do a rescaling, of course, it will also shift to the left and upwards, at least if I tune my exponents, my scaling exponents, in an appropriate manner. So I can write this rescaling in this, using this typical scaling form, where I have a scale parameter which rescales the momentum scale here, the spatial scale, with an additional exponent. It also rescales time, and with a second exponent alpha, it rescales the overall distribution. So in this case, upwards. Yeah, so if I could, now I can of course replace this scale S by my time measured in units of some offset time, T0, to the power beta, and if I insert this, then I can rewrite the scaling form in a way that you see explicitly that the time evolution in this case becomes rescaling. Then in momentum space, it shifts to the left with a factor T over T0 to the power beta. So that needs, of course, that beta is positive, and it shifts upwards with T over T0 to the power alpha. So you can rewrite this because now the time has here fallen out of the evolution on the right-hand side as an explicit parameter being replaced by this offset time. I can rewrite it using this universal scaling function Fs, which just describes the form of this curve, which is then at the particular time defines my number distribution over the momenta, depending on T over T0, and then to these exponents alpha and beta. Now, this is simply a hypothesis now, as you always do in in RG in the first place, so you assume that there is scaling. This is kind of the hypothesis which I expect to be valid only when I have pure scaling of the way as I draw it here. So that's the idealized case.
There's another problem. It runs various scales.
Yes.
But at the same time, at the beginning, you fix the scale and run only the time. So that means you see that P is below a certain fixed scale always. You see what I mean? What happens to the upper limit?
Now, so
if you have fixed, are you going to run the 2 this time?
So of course there's now a typical example will always look like that. Yeah? So there are 2 scales in there. In this case, as I said, these 2 scales. So what I practically assume is I start with such a state and then let it run. And now what I have in mind is I would like to look for solutions which show the scaling, which I draw on the next, which I defined here. This is what I'm looking for. Now, of course, this reduces the problem to only part of the distribution, namely to that part which forgets about UV scale. Now, of course, this one is still there, and I will have to discuss it in a second. You know? So all I'm doing at the moment is I suppose there will be scaling at some point, and I define the most ideal scaling I can have by this scaling hypothesis.
On the log plot, you lose details in the P because you take the log.
Absolutely.
So what about those details?
Which
are really important.
Yes, yes, they will appear. Yeah, absolutely. Yeah. So typically, what I have in mind, and you will see it later on from the practical example, is that I'm averaging kind of over many initial conditions where all these sort of details which remain are averaged out. Yeah? So like here, of course, you would also say, okay, this is an average picture. Yeah? This gives you an average distribution of your particles in a thermal gas. So. Right.
So sorry, do you
yes.
accept this scaling flow to be valid for all time or just for transient?
So for the moment, I'm just defining what scaling means. And what I expect is that this scaling applies exactly on the fixed point. This is the typical hypothesis you do in RG. This sort of, if I set this up and now I want to determine alpha and beta, I'm actually putting myself on the fixed point for the first, forgetting about how I get there. Okay. So that's what the expectation is. You know? That's the idealized scaling case. You know? But to get there, you will see in a minute, it will be slightly more complicated.
Practically, you expect if you do a simulation or
experiment,
that you will never be so close.
Yes.
So you will start building a condensate. That should break the scaling.
Yeah. Wait a sec. We'll come to that in a second. Okay. So to that last step. Yeah? So for the first, I would just set this up as an idealized picture. Yeah? And now, of course, we have to ask, can we actually get there? And if yes, how? Yeah? So what you should keep in mind is that I reduced now all the complexity of the time evolution to a single scaling function, universal scaling function, and 2 universal exponents. Now, in practice, as you now asked already a few times, it's more complicated. Yeah? So typically what you would do is you take your system, you hit it, you make a quench or whatever, you drive it in some way, and then it gets out of equilibrium and starts to evolve. And now the question is kind of in what way can it actually run into such a scaling situation? So this is now sketched here on a single plot, which has both in it, namely the initial distribution, which I suppose I can prepare. Yeah, so for example, by starting with an initial distribution which looks like the thermal one, this is this one. Yeah, so here, temperature, Rayleigh Jeans, and then flat plateau. And then I do a cooling quench, chucking out all these blue particles here at high energies, leaving only kind of this plateau, which now suddenly drops to 0 at some particular quench scale. So that would produce, that quench would produce a distribution which is certainly far out of equilibrium. We have to discuss about how big this has to be and so on.
The initial, the long dashes or the short dashes?
So the initial is kind of the red gaseous, but it's the one already after the quench. So before the quench, it could look like this, like having also these blue particles in it. Okay, but you can do this also in a different way. So in experiment, you would not do this cooling quench. You would rather build up this strong non-equilibrium state in an artificial manner, which I'll show you also in a minute. Yes. Yeah. So typically, what well, I'll show you later an example with the spin 1 gas. We have an instability. That instability produces that initial distribution. Now, for the moment, assume that I can do this. Yeah. So strong non-equilibrium distribution with a very steep fall off at a particular scale. Yeah.
You remove what goes to the right.
Pardon?
And you remove what goes to the right.
Yeah. Now the important thing is that the whole thing wants to evolve, but it needs to fulfill conservation laws by particle number and energy. Yeah, so let's say the area under the curve must stay the same because of particle number conservation. Yes?
Your initial distribution was the thermal distribution.
For example.
And so, fine. So you start with something in thermal equilibrium, and you're taking yourself out of equilibrium just by removing the high energy particles, okay?
Yeah.
And then you just want to see how that evolves.
Yes. Right. So, as before, as I said, so this will certainly like to go back to some equilibrium. So it will want to build off, so to decrease this overpopulation here at this scale, and thereby, and that it can do by sort of shifting the particles to both directions. And now note that these two conservation laws actually impose a constraint which requires that they are shifted to both directions. Namely, if you want to shift these particles, which are here, to lower momenta, they of course lose energy. So if the particles are down here, they have less energy as when they are here. That energy needs to be deposited somewhere, and it can be deposited by just shifting a few particles down here. Because this is double log, you shift quite a lot of particles up here, and you shift quite a lot of energy down here, but this lot of energy is just transported by a few particles. Whereas here there's only few energy transported by a lot of particles.
Your system is isolated.
Yes, that's what I assume for the moment, yes. I mean, that's not the most general. Pardon? Apart from the quench, exactly. Yeah. Mm-hmm. So after the quench, I assume it's isolated.
The number of particles is concerned.
Yes. Yeah, so I'm thinking of these types of systems. Otherwise, yeah, it just gets more complicated. Okay, so what I get is this bidirectional redistribution, which is now here indicated by the arrows. And what you typically will find is, and this is I will illustrate from a simulation, is such a distribution, which in this upper part looks like the one I had on these previous slides, like this one. And eventually we'll be able to show the scaling by with this example here from the solid to the dashed line. Whereas down here I will get kind of a tail with a different shape, which will sort of be shifted out to the opposite side, also for these reasons I just mentioned before, namely energy and particle number conservation. Now down here you can also have rescaling in the opposite direction, but you don't need to.
So there is no rescaling, I mean there is scaling in that part or not?
Down here?
Don't care.
So typically what's going to happen is that this tail quickly thermalizes approximately and hits the UV scale, which it cannot transgress, because the particle number falls somewhere here to 1, and then beyond that it needs to go down exponentially, or maybe with a higher power law if you want. So it will have to stop here, and then all what can happen is that the temperature goes up here. But it's true, you can also have the situation, and I have examples for that, where I see a scaling into this UV direction, which is connected to the scaling into the infrared direction. Right, so this is the general picture which I expect, and now let's actually have a look at a particular example for that. These are now results of simulations for Bose gas in 3 dimensions. And actually what we take, for reasons I'll tell you in a minute, is the 3-component Bose gas, so very much like the spin 1 Bose gas, which has already been discussed here. So we have the typical kinetic term, and then we have an interaction term, which only couples the total densities to each other. Yeah? So it's summed over double indices. So we have here the density coupled to the density, because it's all A and B are both summed from 1 to 3. So this is the typical Gross-Bidevsky density-density coupling. Now here, without any spin-spin interactions, which I leave out for the moment. Now here's an example of the simulations, which looks very much like the sketch I gave you on the previous slide. We put in this initial distribution by hand, yeah, so it's just a box in momentum space. Particles are filled up here to a certain level, up to a certain momentum scale, and phase of the field is actually chosen randomly. Yeah? So there's no coherence whatsoever in the initial state. There's just, let's say, particle number and energy according to this distribution. Then you let it run according to that model, which means you solve the nonlinear Schrödinger equation or Gross-Bidevsky equation for this model, also including some noise in the initial state. Yeah? So as I said here, the phases are completely random, so that introduces already quite some noise. In each realization which we produce, which we run, these phases are different. For that reason, the simulations are not simply solutions of the classical equations of motion, but it's kind of this, what we call the truncated Wigner approximation. So it's a semi-classical statistical simulation of the field dynamics, which should be good and nearly precise, also nearly accurate for large occupation numbers, which we have here throughout our dynamics over the majority of the range of particles. So even down here, it doesn't really go close to 1.
It's only initial conditions.
Yes.
You don't have dynamic fluctuation.
No, we don't. In these simulations, we also did others, but in these here, it's just initial condition is noise. So it's no full quantum simulation, but as all these occupation numbers here are large, the approximation is expected to be actually very, very good. So now what you see is that exactly what I described qualitatively before happens. So you get this bidirectional redistribution. You get a near thermal tail down here, so that's roughly k to the minus 2, which corresponds to a Rayleigh-Jeans distribution. And you get a rescaling distribution here towards the infrared, where we can then go ahead and determine the exponents. So it looks very much like this picture. Actually the underlying conservation laws are exactly as I described.
Sorry, before you move on.
Yeah.
What's the importance of having the 3 components?
Okay, so I already alluded that you can do this with all sorts of other models as well. So with one component, 2, whatever. The reason why we do this, I'll describe in a minute, is because the dominating excitations here will now not be the sound modes of the total density and phase, but will be the relative phase modes between the components. And they actually are just free modes with a free dispersion. You don't have to worry about vortices and defects and all this kind of stuff, but you just get chaotic excitations of those. So when I'm now having a look at how this looks in real space, can you see that? Please, can I shift this somewhere downwards or so?
Yeah, you should be. Yeah,
I can actually.
The far left.
This one. Okay. Right. So what is shown here is I should describe what is shown. So this is the initial state of my simulation. There's again the box in momentum space. You don't see the vertical bar, but it's there. It's just finishing here. This is actually.
So you have a condensate initially too?
No. It's
vertical bar. What's the vertical bar?
So what I'm saying is that they're filled up to a certain. Just remember, I had a vertical bar, which doesn't mean anything. Yeah? So it's just there's a cutoff. Yeah? So this trend stops, and you see just 1 point. Now this is the occupation number distribution, which is essentially the expectation value of the single particle number operator in momentum space. Now, as this all is done on a quadratic box, this is in 2 dimensions. No, actually, in 3 dimensions. These are cuts through 3 dimensions. I'm sorry. We chose periodic boundary conditions. We actually have a translationally invariant system on the average, and I can do the Fourier transform of these distributions and get the G1 coherence function, which just measures the relative phases between 2 different points in the system as a function of the distance of these points. And everything here is angle average, so these are just functions of the moduli, the modulus of distance and momentum.
So why you have so many points that you have different times?
Oh, it's 500. This is this is just one single time, and the box just makes here very high oscillations, which I cannot resolve. It's 512 cubed box or something like that. With the next step, you will see it's gone. These oscillations. This is just the initial state.
This is just one of the components.
Huh? Sorry, this is just one component, but all 3 components are equal. Yeah. So our initial condition is equal distribution of.
I still don't understand that point. There's only one n of k that you started with.
Yes.
So how come I
the
have
others
so many
are
G1 of ours? How come I have so many different values of G1 of ours? You say that
because we have a random phase in here. Yeah? We have a random phase, and so
each
this
realization is different.
Yes, exactly. Yeah. This is the second correlation function we look at. This measures essentially it's a 4-point function, so it measures the relative phase between two components, and the components 1 and 2 at different points in space. So this is actually the G2 function for these relative phases, and that's the Fourier transform again in moments. So it has a similarly it has this kind of near box shape initial, and very sharply peaked function in R space. Now in real space, it's just a chaotic distribution, and the scale here is essentially set by the cutoff of my distribution. Now when we run this, you will see essentially in this distribution what I showed before. And in real time, I should have said what is actually shown here. Sorry, we'll run it again.
So question that I'm sorry, that's one of the 3 components. What would be a low temperature thermal states? So one component is expected to have a low distribution with condensate.
Yeah, we are actually at so low energies that in equilibrium there will be a condensate in all three of them.
Independent.
With independent condensate with some thermal shape. Yeah. Exactly. So that's actually also quite important. So that's why we start at really low energies. It's close to the condensation transition. So in the end, we will actually get condensates with some thermal gas on top.
Couple PEC.
Yeah, exactly. So what you already see is that these. Maybe I should say what is seen on here. So this is the density in real space in the first component, but it's similar in all the others. That is the phase of the Bose field in the first component, and it's similar as in the others. This is the relative phase the relative phase angle between 2 components. Here you see these are always phase angles between -pi and pi and 0 and 2 pi. And this is the cosine of the relative phase, which measures kind of the coherence between the 2 components. So you see where during my rescaling motion, these patches here become bigger. Yeah? So clearly, the transport towards the infrared here in both of these correlations describes a coarsening process in my pattern, which is not really kind of magnetic domain, so it's still sort of relatively chaotic fluctuations, but you see that there are kind of large-scale patterns which essentially, the scale of which is essentially set here by this infrared scale, moving to the left, so moving to larger and larger length scales. Okay, yeah.
All these functions are small but not negligible at the ultraviolet cutoff.
Yes.
So what would happen if you change that in the dynamics? For example, you see the low part.
Essentially nothing. So the only thing what we have done, and this in practice, in practice we have, of course, inserted here a cutoff. Yeah? I mean, this is a classical simulation, so you always need to put a cutoff at the UV end, because if you would shift out this cutoff, it would thermalize at infinitum. Yeah? So you would not see any Bose-Einstein cutoff here, any physical cutoff in such a semi-classical simulation. So this essentially sets our cutoff, and now we have to make sure sort of that this scale is not too small, because otherwise we would introduce too many kind of artifacts. Well, we in fact we make sure that the occupation number stays kind of above the order of 10, or at least above the order of 1.
The reason I'm asking is years ago I talked with David about similar type of simulation. And I asked him how those simulations are stable with respect to the UV cut.
They are not.
They're not.
No.
You see, and that is kind of troubling.
Yes.
Yes. So in this case, it's also not.
Yeah, but I mean, I've discussed this with Matt a long time, because he has spent lots of his time on exactly working this out, kind of what you need to do in order to make sure that you're doing the right thing with these semi-classics. Yeah? So what he has set up,
So in that sense, of course, you get a transition temperature that depends on your cutoff. Okay?
Yes.
But then if you do any thermodynamic measurement,
what's transition temperature?
T lambda, condensation transition. Okay, so we're used to think about T lambda in an canonical.
Only the thermodynamic limit.
So
I'm sorry.
Only the thermodynamic limit.
So it's a classical system. So you have a UV cutoff. You cannot get rid of it. But then you
understand that.
But then if you plot everything in terms of T by T lambda, if you have enough modes, you cannot reach you get to have a cutoff independent quantities. So you see, it's a classical system. So you cannot get rid of it.
So what you typically will find is, of course, you will have sort of a dependence on that cutoff, but provided that the physics happens dominantly in the regime where I have large occupation numbers, dependence on that cutoff will be negligible. So if I shift it a bit, there will be, of course, slight shifts in my results, but only slight shifts, because this is very few particles, and of course the energy sort of will move slightly here if I shift the cutoff.
For example, what will happen to the position of that knee there? You see where the currency changes. It's essentially
independent of that.
So that one can stay where it is, right? But the rest will change.
Yeah, and of course, here at the lower end you will have. So
that's what I understand. So that's what I understand. But I wonder.
No, that's.
So at least that particular part.
Yes.
That's the people notice that.
Yeah.
Okay.
Okay, so what I've shown you now is that this kind of rescaling evolution is essentially corresponds to a coarsening procedure in my real space pattern. You can also see this here in these real space functions. Essentially what we get is a function which starts exponentially at very small distances, and then there will be some oscillations in general. But this kind of exponential start of the distribution tells you essentially that you have a kind of a quasi-condensate developing with a rescaling in time coherence length. Yeah? So the slope of this exponential will change. There will be, of course, details in the long-range behavior due to these oscillations, but essentially what you have is a quasi-condensate at these intermediate times near the fixed point, which will be eventually, and this is not shown in these simulations, disappear when the system then rethermalizes and goes to the condensate. So all these simulations now here, all these times I show you here are still before reaching the vicinity of the fixed point. In order to go away again, I would have now to sort of destroy this overpopulation here in the infrared. And this is actually what's happening at long scales. If I just can't wait as long here, then eventually this part will break down, and you will get essentially here a thermal tail and a single condensate peak, which you can see on this double log plot.
So you say with time that slope will decrease
Well, that's low. First of all, it's a universal power law, which stays as long as you have scaling. But then when you go away from the fixed point, when sort of all these, when the system starts to rethermalize, then it will break down, but in a not in a particular way I'm saying here at the moment. Typically, what can happen is that it starts here to decay, for example, like this, and then goes down like that. But I would have other examples. I just can't run these simulations as long.
No. So that's an indication that this distribution is not thermal, it's running.
Yes.
Thermal will be exponential.
And no, it would be power law, k to the minus 2, like this one, like this case. Exponential comes only down here. Yeah?
The condensate at this time is.
It's on the order of, there's, the zero mode is on the same order as with the lowest non-zero mode.
Then that state will stay there.
And then eventually this zero mode will go up and the rest will go down. Right?
Well, he might measure it. That's what I'm saying. You see, that was my next question. Do you ever see the development of the condensate?
Yes, we do. Not here, but it depends on the initial energy. Exactly.
But the condensate is low.
Pardon?
The scaling you observe is only when the condensate is low enough.
The zero mode in all these situations here is not bigger than here this lowest non-zero mode. It's really like in a quasi-condensate, you don't have a singled out zero mode yet. No?
So you never developed them?
Yes, yes, we do, just not in this one.
Oh, right.
Okay, so let me actually go on. Now, but yeah, of course, always interrupt. Yeah, so I like stuff, even if I don't get through everything yet. So now, once you have this scaling evolution, you can sort of rescale the curves on top of each other and then determine the exponents. It's actually possible to a very nice way. In this example, you get a k to the minus 4 power law here for this overpopulated scaling function, for this shape of the scaling function. And you get actually scaling exponents beta and alpha, and they are, to a good approximation here, they are beta, I didn't write it there, on the order of 1/2, and alpha is equal to 3/2. Also approximately.
So you have fractional effects.
I'll show you in a minute how the numbers actually are. But this is kind of the approximate result which I get out of here. I can say in a minute why this is. Now, first of all, before I go on to argue about the theory behind this a bit more, let me point out that this is to a certain extent different from what we have in the turbulence cascade. So in turbulence, there are cascades which describe direct or inverse flow. In this case, it would be kind of an inverse cascade, which you, for example, know from a 2D classical fluid. Now, here we don't talk about fluid turbulence, but rather about wave turbulence, because we have wave excitations in the system. But also in wave turbulence, you have inverse cascades. And that's actually an inverse cascade in a Bose gas, which has been described since a long time. Now let me point out the differences between this inverse cascade and many of those cascades and the case we have here. So here I'm plotting again kind of a sketch, an idealized sketch of such a self-similar rescaling evolution near a non-thermal fixed point. Now in this case, it actually has two scales on both sides. So you have one scale moving to the left, this powers exponents beta and alpha, and one moving to the right with exponents beta prime and alpha prime. And both of these are connected to each other, again, through the conservation laws. So as I said before, we need to make sure that the area under the curve is conserved, as well as the energy, which is calculated easily, at least the kinetic energy from this distribution, by saying, okay, let's say we take the distribution as a function of k and multiply it with the energy of the mode k, then we get the energy distribution as a function of k. Now, for example, in our case, I showed before, this omega will be simply k squared over 2n for reasons I will argue in a minute, such that the energy distribution is essentially of the same form as the occupation number distribution, just with multiplied with the powers of k squared. Now, the difference between a typical inverse cascade and our self-similar evolution is the fact that the power law is such here, the power law kappa, such that it is between the dimension d of the system and the dimension plus z, where z is the power of the dynamical exponent, or here simply the power of the k-dependence of the eigenfrequency of the mode k. Yeah, so you can actually easily show that when kappa is in between these limits, then the particles are actually concentrated here in the infrared, near this scale p capital lambda, whereas the energy is concentrated at the UV end near the ultraviolet color. This means that you can actually shift both scales independently, thereby conserving energy and particle number because they are apart from each other. Yeah? Because the energy sits somewhere away from the particle number, you can reshape the curve easily to conserve both quantities. Kappa is just the exponent of this power law here in between. Okay? Sorry, that's a bit small. Whereas now, when you go to a typical weak wave turbulence cascade, as I can calculate it for the same type of system, so just the Bose gas, I will find that this exponent kappa is actually smaller than the dimension d for the inverse cascade. And in that case, I have the problem that particles' energy are both concentrated at the ultraviolet end, simply because that power law is too flat. Yeah? You will see that actually if you shift out the cutoff here to the UV, you will get essentially, you will shift out both particles in energy with this cutoff. So they are at the same scales. So by rescaling these two scales, P small lambda and P large lambda, you cannot simply conserve particles in energy at the same time, because the energy, as I said, scales with a different power law. Because of that, maybe I should make this clear by just drawing both in one picture. So if you have particle number like this, then you would say multiplied with k squared, energy would look like this. Yeah? So this should be 4, so you would have probably something like this. Okay, now in this case, the energy is, so this multiplication means that now suddenly the area under the curve is dominated by this regime, whereas for this number curve, the area is dominated by this regime, but it's not the case if this exponent is too big. Yeah, so if it's smaller than the dimension, you can work out easily that this is not the case. And then in that case, actually, there's only one possibility, namely you have to have small scaling violations. And what you can do is you can move out here the scale, but it's actually not a pure rescaling. Yeah? So it's a second order effect. The first order, they get stuck. And to second order, you can sort of shift them both down a little bit and this out. And then you also see that this evolution is not a normal rescaling anymore, as I showed you before with time, but it has this peculiar form. This was shown by Bose in 1991, that actually the infrared limit is reached within a finite time. Yeah, so this factor tau, with which this can be scaled, is such that when t reaches this finite time tau star, then tau is 0, and when tau is 0, with here a positive exponent beta, then actually that's the point. That the reason is because beta is now negative. In our case, it's positive, but here beta is negative, so that the rescaling of p lambda with time looks like t star minus t divided by t star minus t0 to the power beta. So in this case, modulus beta, so that's again a positive number. Yeah? And now you can see that for t equal t star, this factor is 0, and because beta modulus is positive, the whole thing is 0. And this is when the scale p lambda has reached 0, so when we have reached that here on the double log scale minus infinity.
Another question concerning the energy of the mode.
Mm-hmm.
Don't seem to have formulas, right? So would then negative their contributions negative or what?
You mean because of my p flat here? Yeah. So this comes next. Actually, this is why we chose this 3-component gas, because we can't forget about the phonons. They are subdominant. They are there as well. They will create sort of scaling violations, but it's dominated by other excitations.
The phonon will just only appear after the start.
Yeah, well, we have a very chaotic initial condition where everything in there. Yes. Yeah, the coherence needs to build up for the phonons. I know. Yes. Okay, so there's a decisive difference here. Now let us have a look at how we actually can get hold of these exponents here, alpha and beta, for the system. So I go back to my model with a 3-component or n-component Bose gas. We chose n equals 3, but we can do it in a general case for n components.
We need n greater than 1.
No, n is greater equals 1. So yes, okay. Yeah, so actually that's an interesting point. But let me come to the problem now, maybe before I go on. So the main problem we have here is that we have these scaling forms which kind of have this bimodal form. Yeah? So what we need to do is we need to somehow describe the transport in the metal space for such a distribution. Now this is in general done very much like in turbulence theory or wave turbulence theory, which many of you I think are very well familiar with. So what we would like to understand is what are the possible scaling solutions in a kinetic description of this transport as I sketched it before. The problem is that these occupation numbers here are very large. So typically what you would say, I cannot do the calculation because this is way beyond weak wave turbulence. You have actually strong wave turbulence because the occupation number multiplied with the coupling is too large and this simple kinetic approach breaks down. Yeah? So for that reason, we have years ago, this is how we started this business, introduced the field theoretical formalism where we actually do a non-perturbative calculation and derive a kinetic equation from that. That is resumming diagrams to infinite order in a 1 over n expansion and so on and so on. Which actually, as we have shown, is capable of describing such a situation and giving us the right exponents. Now, today I do not want to talk about this because it will be here still tonight, but I would like to sketch a different way how I can actually describe the transport, so this process, in a way which brings me back to weak wave turbulence. The important thing I have to do is I have to go back to a kind of a hydrodynamic formulation of that. So what I'd like now to show you is a way how I can write down a low energy effective theory for this low energy part of my distribution, which is strongly overoccupied, would be way beyond wave turbulence for the fundamental fields, but now will be in the reach of wave turbulence when I go to this low energy effective theory. This is what I'd like to sketch now here on the 2 slides. How is it done?
So you remove the high part.
Yeah, I forget about the high energy part. Actually, I can also treat this in the end, but for this I have weak wave turbulence.
But you have violent conservation of energy.
Yes, so we are only looking now for the first for the fixed point equation. And actually, no, I will not. So this I didn't put out. So of course, what I will still assume is that I will actually assume that these distributions go on like that, and I will have occupation number conservation under these. Of course, it's not.
But you have a different energy.
I know. I know. But don't worry, because we will. I'll come back to that later. Because it's the infrared process, it doesn't care about energy conservation anyway. As I said, energy and particle number are separated. I can have a look at particle number conservation only, so I can forget about that tape. Okay, that's the point. It's of course only an approximation. No? But let's not talk about conservation for a moment. Let's now go to this to the question: how can I actually describe the strong wave turbulence using weak wave turbulence? So what I'd like to do is I'd like to go over to a hydrodynamic description, as one usually does in cold gas physics, at least when one has a quasi-condensate, as I in equilibrium have only in one dimension. So I'll go over replacing the field. Now here I write it down for the classical field by density, so a modulus of the square root of the density times phase. So I go essentially to center coordinates, where I know that the velocity field is now the gradient of this phase angle here in the exponent. That's the typical Madelung, or however cylindrical, circular condensate coordinate transformation. As it is, well used for Bose fluids, where I would like to show the hydrodynamics of the system. So what I get out by plugging these definitions into my equations of motion, so the Gross-Pidevsky equation, I will get two sets of equations. One hydrodynamic Euler-like with some extra quantum pressure terms, and the second one is just the continuity equation describing local particle number conservation. Also, this is very standard way of doing it. Now, we would like to go on and use this to describe the small fluctuations of the system in this low energy regime. Now, also this is standard. What one does is one linearizes these hydrodynamic equations in the fluctuations of the density around some mean value rho A0 and of the phase around whatever mean value. I just choose it to be 0.
And you drop the quantum.
Pardon?
You drop the quantum.
And
You don't
yes.
So it's rho A0 is,
but it's
taken off for the 1.
Pardon?
Rho A is 0 for the flat.
Yeah. So this is
0 or
no. This is not 0. This is now 1 essentially. So it's
so you are doing a rho.
yes. For the first, it's nothing else but rho. Okay. So what I've of course just assumed is that I have a finite mean density. That's it. Yeah? And it's I think perfect approximation for that. Right? So now using these linear equations, of course, I can easily plug them into each other and get the first wave equation, namely for the phase. And that's nothing else but the equation that gives me the Bogoliubov modes of the phase. However, note we have here the slightly more complicated version. There's a sum over all the densities in the different components here, and the delta AB for the K-squared term.
Now we have the Einstein convention.
Yes. Sum over double indices is implied everywhere. Yes. Exactly. So what I get after I diagonalize this system of coupled equations is actually I get, apart from this one Bogoliubov mode in the total density and total phase, I actually get a set of n-1 free modes, Goldstone modes, which describe essentially the relative phase fluctuations between all these different condensates. So note that my overall state around which expand is very simple, namely it has the same density in all components. Yeah? So at least I should have a large density in all components to be able to do that. They don't have to be exactly the same. But if I, for example, take a broken state where I have only a condensate in one component, then of course I would not have these modes. I would only have the Bogoliubov mode. Yeah? So the condition for this is that I have broken my ON symmetry in a particular way, namely that the densities in the different components are sufficiently large.
So 0 is the total density.
Yes. Yes, actually the total density here now in mode A, but it's simply 1 over n of the total density. Yeah?
The interaction strength can be different for different components.
No, it's ON symmetric. That's the important aspect here. Yeah? I mean, of course, you can do a more complicated case, but I just don't want to. Yeah? Simple. Good. So this is kind of standard procedure as you derive from the number of excitations. But now you see, I get also these three modes, and these are the ones which will now dominate my dynamics. Actually, have dominated the dynamics which I showed you. And now comes, so up to here, it's just standard procedure as you would do if you write down also Luttinger liquid for a cold gas. So you have, you get an effective action, which is the sum of these Bogoliubov, this single Bogoliubov mode, and the n-1 Boltzmann modes with different dispersions. That would be just the Luttinger liquid. It's a quadratic and free theory, but it gives you already the linear excitations. Okay? Now, what is now important is to go beyond that in order to describe this transport. And we do it now in a manner which actually assumes that the density fluctuations which were still in there beforehand, that they're actually small and I can integrate them out. Yes, of course, this was still the full hydrodynamic picture with all the density fluctuations, but I assume that these density fluctuations are small and I can argue why they are. And then I can integrate them out in quadratic order, being left with a field theory in the phase only. This is precisely what one does in order to derive these Luttinger liquid type action. But what I also get is now are nonlinear terms, which will be important for describing this transport. So what I get is I get 3-particle and 4-particle vertices, which are now at tree level already depending on momentum. And these vertices couple, so they are describing the scattering of those phase angle excitations. So this is how they look like in practice. So we have dependence here on powers 3 and 4 of your phase modes, and then with some complicated momentum structure. However, this momentum structure is homogeneous in that, so it actually shows scaling with the power k squared, which is now important to describe the wave turbulence of the system.
So the following interaction is related to the phases of the n-1 components.
So initially, of course, we had a nonlinear system in the fundamental fields, but now we have a nonlinear system in the phases. These nonlinear terms actually come all out of the, they all come out of the original kinetic coupling, so they all come out of here. But what is important is that I have a finite density. And of course, then having a finite density around which I expand, I also get a coupling. So it's actually, it's a dual picture. But now after that, I can actually go ahead and write down a weak wave turbulence scaling analysis as you all know it, just using this free part of the theory and these interactions. And when I do that, and let me not go through the details, but what you find is beta is equal to 1/2. And now imposing particle number conservation, I get here alpha is equal to d times beta. So I get 3/2 for alpha. So what I can calculate with this is beta. It describes precisely kind of this, it's not a cascade now, it's this self-similar evolution to the left in time, in a way as you are used to it from weak wave turbulence analysis. Okay?
This is the self-similar evolution.
Yes. Yes, it's actually self-similar, but that can also, I mean, that can also happen in wave turbulence.
Yeah,
so
it's not the Sahara scaling.
No, it's not. No, it's not. It's definitely different.
I think I missed something. So here you basically assume that there is a condensate to start with.
Yes. Yeah, well, not condensate. So I assume that there's a finite large density around which I can expand and have small density fluctuations. So I should maybe say what is this density I expand around. So what I expand around is, remember, I write down psi, I have here psi as the square root of rho, and then there's a fluctuation delta rho. So this is the rho 0, which I expand, times eta and so on. And rho is given by psi, so rho in X space is given by psi dagger X, psi X. So rho in K space is given by a sum over P, psi dagger K plus P, psi dagger psi of P, roughly, maybe some minus signs wrong. So what I expand around is the zero mode of that. So I take rho of 0, and that is the sum over P of psi dagger P psi T. So it's nothing else but the area under the curve. It's simply the total density. This is what I expand around. This is the standard way how you do it when you have a quasi-condensate. So if you have a large occupation of the low energetic modes, but no single condensate. So all, of course, this distribution is dominated by these low energy modes, and so you expand around them. In the density, that's why you don't have to care about the phase. It's different than what you do usually in a condensate, where you expand around a field expectation value. You don't do that here.
Yeah, because the point that I was confused is that you actually get it for both spectrum, just like the zero temperature. So you are saying that you now rely on the quasi-condensate.
Yes, the quasi-condensate also has probability of acceleration. Yes.
Now then, my second question is about the way that it's probably that I'm not sure whether it affects the final result of the details or whatever. The density part, I can understand that you can ignore the amplitude fluctuation, so that's the keep on the phase.
That's right.
But for the relative phase mode, then it's actually very tricky for the UN system because it's symmetric, the amplitude would also fluctuate. So you throw that away from the relative.
Well, the only thing what you throw away is the density fluctuations.
No, but the relative density fluctuation you also throw it away on this line.
Yes, because I integrate out the single density fluctuations, so also you integrate out the relative fluctuations. Absolutely. I mean, this is what you can do with it. So you need to make sure that the density fluctuations are not overwhelming the system.
Yeah.
And this is what I assume for this low energetic part. But this is the typical thing which one always does if one has this kind of quasi-condensate-like distribution. So no zero mode, but all the particles sit in the lowest non-zero modes, like you have in 1D. Remember in 1D, the G1 function of R, which I also plot, has exactly this form. It's exponentially decaying with e to the minus R divided by the coherence length psi. And in order to calculate that distribution and the excitations on top of this system, you do exactly this procedure. And the results will also be bioprobability of excitations and the like.
Yeah, because right now there's no restoring force for the relative density fluctuation. Because it's UN. Mm-hmm. So the amplitude, I thought that it would be still fluctuating, not just the phase.
Yeah, certainly, there are small fluctuations. I don't say that they are away. I just integrate them. So I assume that I can neglect. I can actually argue why I can neglect. Yeah? So all I neglect are the delta rho to the 3 and 4 and so on terms. So I take into account only the quadratic terms of the delta rho fluctuations. They are there. They are just integrated out. Yeah?
Okay.
They are approximated to Gaussian order. That's what I do. Huh? They're not completely gone. Yeah, so I presume when I have, for example, defects or many defects in there or many domain walls or so, I cannot do that anymore. Yeah? But in this approximation where the density is essentially flat and all what happens is that the phase fluctuates, I can do it.
Don't you have to assume that the lowest few modes which are highly occupied are phase locked? Because
no, that's exactly the point. So I can. Oh, actually, no. This is what you. I mean, this is how they are phase locked. Okay. And this is what you see also in our simulations. They're exponentially phase-locked. They're not completely, of course, coherent, yeah? But the coherence falls off exponentially. But that is included in this approximation here. So I actually get, out of this approximation, I get this exponential form. I don't get the oscillations of the function. These are more details. So I showed you it's not a pure exponential, but there are then some oscillations at large density, at large distance. I don't get them, but I get the exponential. Okay, so this is essentially how we do it, and I don't want to sort of give more details. Probably I should. No, the time's probably up.
Yeah.
Yeah. So here's maybe the final numerical result, how the exponents look like, which we extract from the dynamics. So you see, this is for the G1 function. We have actually so. Well, what we did is we took this G1 function as derived from the numerics, and then we did a Taylor fit to this exponential curve, which is numerically a bit hard, so it has big errors for the higher coefficients, but at least for the lowest coefficients, it shows that they are one of them here, the second one, almost scales all the time as 1/2. The other one approaches it. The same happens for the G12, so at large times they seem to all scale roughly with the same exponent. So it looks like as we are building up a better and better scaling function to large distances. So this is essentially what I wanted to say about that. Now, now I should probably stop before the commercial break, or we just do the commercial break and that's it. So what, yeah, we can, I don't know, oh yeah, much to go now. Okay.
Let's I mean, if you have a quick message, say it, then we can resume this afternoon.
Yeah, so the message is essentially that there has been very nice experiments in Heidelberg being done in a spin-1 Bose gas. Yeah, we quench it, we observe all sorts of excitations. It's a quasi-1D system, so we can actually image it very nicely. And the data shows very nicely scaling with exponents beta equals 0.5 and alpha equals roughly also 0.5 because it's quasi-1D. So this is essentially an exponential, an experimental result at least corroborating this theory. So this would be the commercial break, exactly. Then the rest is turbulence, but that's another story.
Okay, thank you very much. Any final questions? We can chat a lot more this afternoon.
So that means no question, or
It's a good question. It's a very quick question. So the alpha here is different from that because that's 1D.
Yeah, that's 1D. So actually, the general result here is you can show it simply. I mean, you have to make sure that number is conserved, and then that gives you the dimension into this relation between alpha and beta. So alpha, essentially, alpha divided by beta is the dimension. And here we are quasi 1D. It's not completely 1D. Very close to 1D.
0.33 is a half.
Huh?
So 0.33 is a half.
Yeah, but there's also narrow there. There's, I think they have nicer results now, which are closer to what there's also lots of particles, and so this comes.
Okay, there's just another fraction. I usually think of.
Yeah. Oh, we should be careful with that.
Can you do simple, like, can you see this from 1D GP or truncated Wigner calculation?
Yes.
So that's something for students to try.
So to do this here in truncated Wigner was really hard. We really so the experiment itself was really the hardest I had so far, but it's exactly at this limit where truncated Wigner starts to break down. So they have just too low particle numbers. So we became too much dependent on these, especially transverse cutoffs and so on. Still, it was always in the realm of I mean, it's just too cutoff dependent.
Strictly 1D, you have issues.
Now,
the GP equations integral.
Strictly 1D we could do, yeah, but strictly 1D, we find for a spin Bose gas, for a speed of Bose gas with these spin interactions, we get solitons and domain walls, and they actually dominate the system, and then we get actually 1 beta equals 1, so the exponents change.
It's neither quasi to quasi same business.
Yes, exactly, and now they actually can even create also solitons, so they know that they due to the smaller 1D, they actually yes. Yeah. Yeah.
After questions, so I'll just ask.
Oh, any questions remotely?
I can't hear anything.
Yeah, we have to check that. Okay, thank you. So we'll meet back at 3 o'clock for some more discussion. Okay, and then lunch for people who are new, we'll typically meet just by the elevators at about 12:15 and head out again for lunch. All right, great, thanks.
Good. Thanks.